To watch this video, you're going to want to get yourself a periodic table. So what we're trying to do is arrange electrons around the different types of atoms, different elements in order. We want to arrange those electrons in orbitals, atomic orbitals. So in class, we laid out some different examples of atomic orbitals. The 1s orbital, which is the lowest energy orbital. The 2s, which is larger and therefore higher energy than the 1s. And the set of p orbitals in the second energy level. So this is an energy level diagram. And so the energy is something expressed in units of joules or kilojoules. And we're showing this sort of listing. Low energies down here, high energies up there, and all our energies are negative, so like 0 is like up there. So we're getting more and more negative, low energy. So we've got the energy levels 1, 2, and 3 represented here, but we could have higher principal quantum numbers, 4, 5, 6, 7. There's no limit. You just need the energy to get to those levels. Now the sublevels in the energy, the n equals 1 energy level, there's only that one sublevel. That's because the L quantum number is 0, which is the letter S. So there's just the 1s type of orbital. That 1 represents the n, the s represents the L quantum number. In the second energy level, we have two types of sublevels, the s-type orbital and the p-type orbital. They have different shapes. This is spherical, this has a pinch. And of the p orbital type with that pinch, there are 3 orientations because the m sub L quantum number is -1, 0, +1. So altogether, there are 4 orbital types in the second energy level. In third energy level, we have even more types. We have the S, we have the P, and we have the D. There's that set of P orbitals, 3 of them. And then the D orbitals, there are 5. Oh my goodness, there's so many orbitals in that third energy level. What are orbitals? They are spaces that electron wave particles spread into. They're 3-dimensional, they have shape, they have size. That's how we're arranging the electrons in these atoms, in these different orbital shapes. Okay, so let's start with hydrogen. Neutral hydrogen has 1 electron. In the ground state, its lowest energy state, we would place that electron in a 1s orbital shape. So we represent that electron, we can't draw it, so we just represent it with an arrow. So I'm going to use an arrow to represent 1 electron. So that 1 electron, ground state hydrogen, is in the 1s orbital. So I'll list it here. I'll say there is 1 electron in the 1s orbital. Helium, number 2 on the periodic table, 2 protons, therefore 2 electrons for neutral helium. 2 electrons. Okay, I can put up to 2 electrons in a single orbital according to the Pauli exclusion principle if the spins are paired. So up-down arrows represents 2 electrons and they're paired. So I'll list that over here. 1s squared, or 2. 2 electrons in that 1s orbital space, which is spherical. So our 2 electrons with their opposite magnetic effects are spreading into that 1s orbital. Now let's try our next element on the periodic table. Number 3 is lithium. So lithium has 3 electrons. Where do they go? Well, we can put up to 2 in this orbital. So I got a 3rd electron, can't put it there. I'm gonna have to start putting it in the next lowest energy orbital, which would be this 2s. So I'll put an arrow there. 1, 2, 3 arrows. So let's list that. We've got the 1s2, and in the second, the 2s orbital, there is 1 electron. Great. We're arranging electrons around the center of lithium. Let's just, we have this list. Let's just draw it because we like to do art. So here's lithium with its 3 protons. It probably has a neutron or 2 in the center. And then in the 1s orbital, which is spherical, 3 dimensions, it's got 2 electrons spread in there. I can't draw them. We represent them with an arrow. But drawing them, they're like these waves that are spread and contained all within that orbital. Whatever that looks like, that's just an artist's rendition. And there are 2 of them in that space. And in the 2s space, which is larger because that n quantum number now is bigger, a larger space. All within that space is another electron that's spread out. And look, it's kind of like all overlapping. Two of these electrons only go to a certain extent, and then that third electron goes to a larger extent. So this is the arrangement. I mean, Bohr never imagined this. This is the arrangement of those 3 electrons in a lithium. It's beautiful, but I'll erase it. Let's do another atom. What is number 4? So number 4 is beryllium. So beryllium is at least going to be 1s2, 2s1, but we got another electron. We're going to put that in that second energy level s orbital. But to do it, I got to make sure pair the spin. So I got up and down arrows. So everybody's paired. I can't put any more in that. But that's okay. Beryllium is fine with that. It only has 4 electrons. So after beryllium, we have boron, number 5, if you're looking at your periodic table, 5 electrons. So I at least need these 4, 1s2, 2s2. And where do I put my next electron? Well, according to our rules for building up these electron arrangements, it's also called the Aufbau principle. The 5th electron, I got to put in the next set of orbitals here. I've got a whole set. They're all degenerate. Degenerate means same energy value here, whatever that is in joules. My 5th electron can go in any of these. They're all the same energy, so I'll just stick it in the first one. So that's a 2p. So over here I'll write 2p1. All right, that's boron. Now let's do carbon. Carbon's number 6, 6 electrons. So it at least has this, 1s2, 2s2, 2p, and I've got one more electron, so instead of a 1, I'm going to put a 2. I got 2 electrons in the 2p. How are they distributed? Well, here's our 5th electron. I've got a 6th electron. Where do I put it? Hund's rule. Hund's rule tells us don't pair it here in the first one when there's another orbital with the same energy available. So when you have degenerate levels, you half fill them before you start pairing. So there we go, and that shows 2 unpaired electrons. I might as well remark about that. 2 unpaired electrons means this carbon atom is predicted to have a magnetic effect, paramagnetism. So we should be able to see that experimentally. Well, that's great. Whereas beryllium's got everybody paired. So that would be diamagnetic. Okay, that's carbon. Let's try nitrogen. Next one, number 7. 7. Oh, I gotta add another electron. So 1s2, 2s2, 2p. I'm gonna put 3 electrons in this set of p's. My 3rd electron, though, I'm gonna follow that Hund's rule. I'm not gonna pair it up yet. So I have 3 unpaired electrons. Nitrogen is even more paramagnetic than carbon. Wow. Okay, so that's nitrogen, oxygen. Oxygen's number 8. Look, we're just going in order. 8 electrons. All right, so my next electron, I've got 7 represented in this energy level diagram. My 8th one, where do I put it? Oh, I can start pairing now. So they're all equivalent. It doesn't matter which one. I'll just pick one. Now, oxygen only has 2 unpaired electrons, so it's less paramagnetic than nitrogen. So we write 1s2, 2s2, 2p4. So these horizontal things that I'm writing here, these are called electron configuration. It's like a listing of what we're seeing here in the vertical energy level diagram. Energy level diagram, electron configuration. Okay, so after oxygen comes fluorine. So oxygen's 8, so fluorine is number 9, 9 protons, therefore 9 electrons to arrange. All right, so we've got 2 down here in the 1s, 2 more in the 2s, so that's 4, and then 5, 6, 7, 8, 9. I've got 9 arrows there. So that's a total of 5 in the set of p orbitals. Look at that. So I say 2p5. Beautiful. All right, neon. Neon is after fluorine. Yeah, neon is number 10. One more electron. Okay, so neon has one more electron. It looks like there's a spot right there waiting for neon's 10th electron, and that fills the set of p orbitals. So let's write that. Electron configuration, 1s2, 2s2, 2p6. That's a very interesting electron configuration because we have filled the entire second energy level, which only has s and p orbitals. It takes 2, 4, 6, 8, 8 electrons to fill this second energy level, to fill a set of s and p orbitals. And so if you look on your periodic table where neon is, neon's in that last column. That's main group 8 or column 18. Main group 8, those are the noble gases, 8. It takes 8 electrons to fill this set of s and p orbitals. Maybe there's something special about having a full set of s and p orbitals that makes something like neon and noble gas very unreactive and stable as is. Whereas all the other elements, they react. They don't have filled s and p orbitals. But that's a story for another day. Hope this helps.